We've been talking about recipes, mechanical processes, how-to methods for capturing ways of getting the computer to do something for us. Now we can ask the question, how do we actually get that recipe into a mechanical process inside of the computer? What kind of things will we need to have the computer do that work for us? Do that little Heron of Alexandria algorithm for computing square roots. We've actually got a couple of choices here. First one is we could build a machine specifically to compute square roots. Might sound odd. We probably don't need something quite that particular, but in fact, early computers were exactly this. They were instances of what were called fixed program computers. And a fixed program computer was something that did a specific calculation and was designed to do exactly that. In fact, you've seen a fixed program computer. A calculator is exactly that. It does a set of arithmetic computations. That's all it does. It could be more complicated, and in fact, some of the early computers were. At Nassau and Berry in 1941 built a computer for solving systems of linear equations. And even despite the fact that the technology wasn't quite as sophisticated as it is today, it did quite well at doing that. During the war, Alan Turing, one of the most famous computer scientists, built what was called the bombe, which was used to decode Enigma codes during World War II. Again, a computer built specifically for that purpose, but solving a very complex task. The problem with a fixed program computer is that it does only that thing it was designed to do. What we'd really like is a computer that can do anything we tell it to do. And for that, we want a machine that can both store and manipulate sequences of instructions. And those are called stored program computers. And that's what almost every modern computer is. It's a stored program computer. All right, so what does that say? What does it mean? Well, the idea behind a stored program computer is that we can take a sequence of instructions. We're going to talk in a second about how we create them. But a sequence of instructions, think of it as a program, that is going to capture the steps of our algorithm in order, and we're going to be able to input that sequence of instructions inside the computer. That sequence of instructions will be built from a predefined set of primitives. That goes back to what we talked about earlier. Most cases, those primitives will be very simple things. Simple arithmetic, simple logic, simple tests on both numbers and characters, and the ability to move data around inside of the machine. Very primitive operations. We're going to see how to use those in a clever way, but that sequence of instructions is what we're going to read into the computer and store there. Once we've done that, then inside the computer there will be a special program called an interpreter. And that program basically walks through those sequence of instructions in order, executing each one in turn. It's going to use the tests to change the flow of control through the sequence and to decide when to stop once we're done. But it's going to simply execute a very simple set of instructions. So the idea is we can read or load the instructions into the computer. We might be able to change them around, and then we can ask the computer to start at the beginning and walk through the sequence, executing some computation. Let's look at that in a bit more detail. So here's a simple architecture for a computer. It's got a memory. It's got what's called an ALU, or an arithmetic logic unit, which is going to do those primitive operations for us. And it's got a control unit that keeps track of where things are and asks the ALU to do work. So when we read in some code, a program, it's basically going to create a set of instructions up here in the memory. And inside the control unit, there's a special thing called a program counter that initially points to the first instruction in that sequence. When we ask the program to run, when we ask the interpreter to execute the program, it starts by going to that instruction and executing it. And that instruction will typically be something that takes some value out of memory, runs it into the ALU, does some computation, and stores it back in memory. Having done that, the program counter increases by 1, which means it goes to the next instruction. And it executes that instruction, which again typically will be to take some values in memory, run them through the ALU, do a simple computation, and store them back here. And it simply keeps doing that, moving through the sequence of instructions one at a time, doing those very simple arithmetic and logic kinds of computations. Every once in a while, we'll get to an instruction that is a test. It's going to compare a number, see if it's greater than 0, for example, or compare a character. But it's going to do a simple test. If that test turns out to be true, that test is going to actually change the program counter, causing the system to jump back to or jump forward to some other place in the code, changing where we are in the code. And it's going to keep doing that. And it will do that until, in fact, it reaches a point where it says, I'm done, at which point it will output the result here. Those are the basic elements of a computer. A control unit here that has us follow through a sequence of instructions up here, causing data to flow through the ALU and back into memory, and occasionally using tests to jump around in the code. And we're going to see very shortly how to start building up programs to do exactly that. But that's what the computer does. Okay, that sounds neat. So what are the primitives? Essentially says if we can have a stored program computer, we need a set of primitives. We're going to need some way of controlling them, which we'll get to. But what are the primitives? Well, it turns out that that same guy, Alan Turing, showed that using just 6 primitives, it's possible to compute anything that's computable. That's amazing. 6 simple primitives are sufficient to compute anything that's computable. And in fact, we refer to that property as saying that any computer, any interpreter that has that property is what we call Turing complete, which, by the way, says anything you compute in one programming language, you can compute in any other programming language. Now, having only 6 primitives sounds cool, but it also sounds like, man, if I got to program everything by reducing it down to some really large sequence of primitive operations, this is going to be a serious pain in some parts of the anatomy. And it is. So fortunately, modern programming languages have a more convenient set of primitives. And in the next lecture sequence, we're going to start talking about what those are in Python, the language we're going to use. Not only do we have a more convenient set of primitives, but a key thing a programming language will have is some way of being able to abstract methods. That is, take a description, that sequence of code that we've written, and use it to create a new primitive, thereby adding to the set of primitives that the system can use. But nonetheless, as we've seen, just starting from 6 primitives, we can build up an entire array of computation, and anything computable in one language is going to be computable in any other programming language. And that's amazing.